This is a quick lecture on quantum Fourier transform and phase estimation. It's based on book chapters 7.1 and 7.2 and Qiskit section 3.5. As quick updates, most of you should be working on the homeworks appropriate for the class that you signed up for. I posted a link to notes on hints for homework 6 on Slack. You should, I think a couple of days ago on Monday. The aim is to actually record them as a narrated lecture, but that's coming later today. The most important thing as far as updates is a reminder that we'll have a guest lecture this coming Friday on the Shor algorithm. And this week we will, work up towards the Shor algorithm and maybe even cover it a little bit. So this lecture sets up the stage with quantum Fourier transform, and Shor algorithm is sort of coming next. And on Friday you'll have another lecture on Shor. On the basic quantum mechanics side, we are going to be doing the harmonic oscillator, and again, the lecture for that is forthcoming. Okay, so the plan is very simple, is to describe how the quantum Fourier transform works. These are the slides for Monday, the sort of basic discussion of periodicity as the chief application of Fourier transforms in physics and mathematics. This is a cartoon. This is supposed to be a cartoon of a crystal of salt, also known as rock salt. It's the basic table salt that we eat. The sodium chloride molecules are arranged in a periodic pattern. There is the sort of the spacing, and so this is a repeating pattern. It repeats forever in space inside the crystal. And the question is, how do we measure the spacing? Because it's usually microscopic. It's a few angstroms, invisible to the naked eye. And so the trick that is probably about 100, maybe 150 years old by now, is scattering. And the idea is this sort of mathematical sort of underpinnings of this is that in addition to real space, there are infinite number of different spaces to which you can rotate. It's a basis rotation. If you think of it as linear algebra, it's all rather simple. And the most useful basis is the so-called Fourier basis, named after the mathematician who has worked on transforms into that basis. In physics, we refer to it as k-space. So there's real space, position space, and there's a space of wave vectors, or k-space. Now, because these are complete, these spaces represent the information completely, so all the real space points get transformed to Fourier space, they're of equal dimensions. Right? Here are some quick definitions, especially those of you who haven't seen Fourier transforms. You would probably benefit from finding more information. But the basic idea is that for periodic functions, the Fourier transforms are especially powerful, because what happens is, so the thing that's enclosed in the red box is the Fourier transform. If the function is periodic, then this this sum upon real space is broken up to a set of identical smaller sums, identical in the sense that the function repeats itself, so it's identical, but the phase factor doesn't repeat itself. And this is what basically regrouping this sum into a sum over what's called a unit cell, where the function doesn't repeat itself, and then the sum over several unit cells, which I now count with little n. You can see how you can factorize a Fourier transform for periodic function into a factor which knows about the shape of the function. It's called the form factor, and a factor that only knows about the periodicity itself, and that's called the structure factor. And so this factorization allows you to somehow focus on the structure factor by itself, because that contains the simpler information about just the periodicity. And it's possible to demonstrate the structure factor for a large number of points when a large number of points is included here, the structure factor becomes sharply peaked around a position in Fourier space, which is Rk over n. Okay, this is that alone would not be sufficient to describe Fourier transforms. This is just a summary. If there is interest, I would be very happy to give additional reading on Fourier transforms, maybe even exercises. I feel that those of you who have not had them and reached this far in your education should really worry and fill in this gap. And I'm happy to help with that. But for now, I'll move on. The quantum Fourier transform is simply a matrix that moves you from real space basis x into Fourier basis y. And the inverse of the transform is just the inverse of this matrix, and you can see that you can do this by essentially putting minus signs, in the arguments of these exponents. Now, it's a quick example. If your space size is small, if you're only dealing with 2 points, then all of these phases simplify to just simply plus and minus. And you can see that the Hadamard transform that we've discussed before, which maps 0 to 0 plus 1 and 1 to 0 minus 1, is actually an example of a Fourier transform. Okay, so one of the things that most of us like to see are reminders about base changes in representing numbers. Unless you're a computer scientist who would do this regularly, as a physicist, I'm most comfortable with decimals, which is to say base 10 numbers. But that's just a historical accident, of course. Just very quickly reminding you about binaries. If you represent a number in whatever bases, there are significant digits. So now for simplicity, we're going to talk about numbers that are between 0 and 1. So here's one such number. So x1 is the most significant digit, x2 is the second most significant digit, and so on and so forth. The actual value of this number, if we're dealing in binary, is this sum. So you can check. Here I inserted a quick comment. If you take this x1, x2, and so on and so forth as an integer, omega is really just the ratio of two integers, x divided by 2 to the n, where n is the size of x. Right. Another way of writing it is that each significant digit multiplies the whatever base to the negative degree of the integer. So here's another representation. The most important thing that we're going to use next is that you can move the decimal point, right? By multiplying it by base to some positive power, you can move the decimal point to the right. And so that basically, this is sort of represented here. And the reason why this is important is because all of these omegas and whatnot, they will show up in the exponent multiplied by 2 pi I. I should remind yourself that 2 pi I times an integer is 1. So that means that if you start with omega, you multiply it by 2k, the object that you're left with in the exponent is going to have the leading significant decimal places truncated. Basically, k, by choosing k, you can choose where to truncate your leading decimal places. Okay. All right. So another preliminary piece of information, which is rather non-trivial, especially as compared to the previous slide, is the so-called magic formula. That's not the official denomination, but it is quite surprising the first time you see it. Certainly when I first time I saw it. And this basically states that the state that we obtained by this superposition, from which we're going to try to read off, infer the x, just looking slightly ahead. This state, which is a huge superposition of different states of y, is actually very simple. To be precise, it is a product state where each of the qubits in which y is encoded, each of the qubits is twisted with this extra phase, so to say, and the amount of the twist depends on the digits of the input parameter x, input number x. And importantly, it's in the product state, and product states are easy to manipulate. So you just operate on individual qubits, and so what you see is that all of this information has been encoded in how individual qubits of y are twisted. Okay, and there's a certain pattern that we will appreciate better if we start with small, rather than talking about general structure. We can talk about n equals 1, 2, 3, and you'll see how the structure is very natural, but it's rather remarkable. So this formula can be proved generally, and so here's a proof. So what we're trying to prove, this is what we start with, and the proof essentially proceeds by writing out this product x times y in binary, right? So if we write this out, if we write y out in binary, and we write what you will see is that the different digits of y will operate differently. You can see there's a 2 to the L, and so if we now think back to the review slides on essentially base 2 sort of arithmetic, or base anything. So in this case, when you multiply 2 by L, you actually move the decimal place. And now when you exponentiate this number, the integer part drops out, right? Everything beyond the decimal stays, but an exponent of 2 pi I times an integer is 1, and therefore we can just drop all of this out and replace it by 0. Okay. If you didn't catch that, that's okay. Both Qiskit has a proof as well, just more or less along the same line, so you can look at that. I think this is an exercise problem in the textbook, in the KLM textbook. Anyway, let's start with a quick warm-up for n equals 1. And I think the idea here is that with these warm-ups, I'll go progressively faster. So n equals 1 is pretty trivial, but I have a slide on it. So let's just start writing it out. N equals 1 has just one digit. So the number that we're trying to infer is O.x1 in basis 2. So that just means that it's x1 divided by 2. Right? For decimals, it would be x1. In a base 10 representation, the number would have been x1 divided by 10, i.e. 0.1, but we're in base 2. So that's you plug it in, you do the math, the factors of 2 cancel, and you're left with this state. So root 2 out front for normalization. If y is equal to 0, the phase factor is 0. If y is equal to 1, the phase factor e to the I pi x1. E to the I pi is minus 1. So you can see that if x1 now is 0, you'll end up with 0 plus 1. If x1 is 1, you'll end up with 0 minus 1. And what you see is that these superpositions are old friends. They can be decoded by applying the Hadamard gate. In particular, the Hadamard gate will move this, will transform 0 plus 1 to 0 and 0 minus 1 to 1. So you can see that the state that we wrote can be decoded with trivially by just applying the Hadamard gate. Okay, now we move on to case of 2 qubits. And as you can see now, this is complicated enough that we have to break it up into cases further. Well, before we do that, let's start by applying the magic formula to rewrite the sum over 4 basis states. Remember that we're dealing with 2 qubits, so y runs from 0 to 3, which is, say, state 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1. Okay. Now, if we use the magic formula, since it's been already proved, we don't have to marvel at it. We can just use it. This is the formula. And it still looks complicated, but now if you start subdividing it into cases, the easy case is when x2 is equal to 0, then the first qubit is in a 0 plus 1 superposition, and that we can decode with a Hadamard gate trivially. The second qubit is in a superposition 0 plus e to the 2 pi I point x1 times 1. So you can see that the first qubit we can decode with a Hadamard immediately, and we'll find out that it's in a 0 state because it's a, if x2 is equal to 0, it's a 0 plus 1, which gets them to 0. But the second qubit is in a state that we already figured out how to decode for n equals 1. It's the state 0 plus 2 pi I point x1 times 1, and that we can decode with a Hadamard, and that can end in either in 0 or 1, and that'll tell us what the second qubit is. So, and this is what this note should be saying, right? So if x2 is equal, if we apply a Hadamard gate to the first bit and we find out that x2 equal to 0, the only other thing we have to do is apply the Hadamard gate to this one, and we're done. Okay. And I'll collect all of these sort of cases in a single diagram when I'm done treating the second case. The second case is when x2 is equal to 1, and this is where you see this is where you'll see something new, because so far we just used Hadamard gates. If x2 equals 1, you can see what our challenge is. Because previously, when x2 was 0, this more complicated phase with 2 significant digits was reduced to point x1, nothing, right? Whereas now it's point x1, 1, right? And not thinking about this too much, we could say that, well, let's just remove this 1. How do we remove the 1? Remember that because of this product structure, the first qubit is in a 0 minus 1 state, because x2 is equal to 1. No, sorry. The first qubit is in the minus 1 state. Sorry, I should have written that in here. The second qubit is in this state, so now we basically have to figure out how to fix up the state of this qubit so we can detect it. We can detect x1 using Hadamard as before. And the simple thing is to simply subtract off the second significant digit, which is now 1. And the way to do that, right, because you see you have a phase on 0 and you have a phase on 1. So you want to apply a phase rotation on that qubit that will leave 0 undisturbed, but will take away the 0.01 of the phase of the second one. And the qubit that you need is here. All right, so if you think of the gate as represented by this matrix as operating on the qubit, so you can see that this is the qubit, right? You can convince yourself that simply going in and having this diagonal matrix element, which is minus 2 pi I 0.01, will essentially, you can just do a matrix vector multiplication to see that this 0.01 will remove this 1 in the second decimal place to give you the state. And this state is our friend. We already figured out how to analyze that state. Okay. Let's dwell a little bit more on this, what this gate is. It's called a controlled rotation gate, similar to controlled NOT gate. Remember that the sequence of steps, we first measure the first qubit. If it's 0, we do nothing. We just apply Hadamard. If it is 1, then we do this controlled rotation. So it's going to have a structure. You can see I wrote this at the bottom of the page. Just like there's a control C0 gate, this is a CR sub K, which is a 4x4 matrix. And the top corner, top 2x2 sort of portion is the identity. It's the do nothing corner. The bottom 2x2 corner is this rotation matrix that we've been already writing. And just to generalize this, the rotation matrix that we applied was 2 pi I 0.01, and that's equivalent to rotating the second decimal place. And so the notation here is K refers to which decimal place you want to rotate. Okay, so it's 2 pi I, and again, because we're in binary, 0.01 means 1 over 2 squared, because it's the second decimal place, but more generally, it'll be 1 over 2 to the K. Okay. All right. There is an interesting aside that's worth just making sure that you understand. And it's trivial if you are comfortable thinking about all of these things as just matrices. It might seem mysterious if you are trying to kind of think about this intuitively. So obviously I prefer to find the way that makes it trivial, right? But sometimes it's good to think intuitively as well. So the point that I'm trying to make is that this matrix, once you put in the physical labels, and by physical labels I mean what these 4 states are, there are 0, 0, 0, 1, 1, 0, 1, 1. Remember, this phase operates only when the first qubit is in the 1 state. When it's 0, it doesn't do anything. That's the identity part. Now, what you observe is now that if you precede this thing with a swap operation, you will exchange the values of the first 2 qubits. Of the 2 qubits, there's only 2 qubits. So 0, 0 will, so if you perform a swap first, 0, 0 will be unaffected, 1, 1 will be unaffected, but 0 and 1 will switch places. However, because the matrix elements in the CR gate are identical here on the diagonal, it's an identity, essentially, on the diagonal in the subspace, it means that switching 0, 1 with 1, 0 actually doesn't change it. And the implication that it has is that if you operate, so this is sort of reminiscent of the phase kickback sort of a trick, except here it's not a trick because we're not, we don't have to insert any extra things. It's just an identity. That using top gate qubit channel as a control and bottom as a target is equivalent to switching it around. Again, it's not obvious which gates do this or not, but this is sort of the constructive sort of a demonstration of that. All you have to do is just swap qubits and ask whether the matrix is invariant or not. All right, let's come back and finish up the n equals 2 case. So we basically need to take the state of the second qubit and multiply it by this matrix, but because of the minus sign, because remember we're trying to subtract off the second decimal place, it's actually the inverse of the R2 gate, right? It's 2 because it's the second decimal place. It's inverse because that's a minus sign. You can convince yourself that if you have a diagonal matrix like this, inverse of this diagonal matrix is just inverse of the diagonal matrix element. So inverse of 1 is 1. Inverse of e to the something in the exponent is e to the minus that in the exponent. That's the minus that. So finally, let's put it all together. Because of the magic formula, this is the input that we've got. When we put this in and we apply one Hadamard operation, we get the state of this qubit will be 0 or 1, depending on the value of x2. So then we're going to use our conditional R2, 1 over R2 inverse gate. And what that will do is that'll remove this x2 from this decimal place. And then it becomes a 0 plus minus 1, depending on the value of x1. So you can see that with a second Hadamard, you will essentially fix it up that the output of this will be the digits of the phase. Okay. So you can now think about the pattern. The pattern is, this is what we described before. This is the N2 one. So you can now see that the output at this level, let me draw it with a, at this level, let's see, at this level, this was the n equals 2 solution from before. So it's very nice and hierarchical. Basically, you're going to apply n equals 2, you solve the problem up to this amount. Then then what you need to do is that you're going to have a phase here which has the x1, x2, and x3 which you've computed from here. And so what you need to do is you need to now go in and remove those digits. And you're going to remove them the same way you removed them before by applying inverse R2 and R3 gates. Do them in either order, it doesn't matter. And then again, you can read off what x1 is with the Hadamard gate. This is it. So you can see how you can scale this up to n4, 5, 6. You're just basically going to nest this structure on it. Like whatever previous n that you figured out, you're going to have that many inverse R gates followed by a Hadamard. Okay. So that allows us to compute the number of gates that we need for the circuit to operate. So for one gate, it was 1, just a Hadamard. For 2 gates, it was 2. For 3, it was 3. You can see that the number of extra R gates that you're going to add will be whatever the previous value of n. So you can basically see that the number of total gates will scale as n squared, because at each adjacent, if you were to take a circuit and add an extra qubit to it, the number of R gates that will be required will be of order n. Okay. All right, so we've got an order n squared algorithm for computing omega in this form from the state given that. So it's basically the output of the algorithm is to take the state and spit out omega. Again, I'm going to remind you of the binary sort of notation that omega is between 0 and 1. Okay, and it can be thought of as an integer represented in the binary x1, x2, x3, xn divided by 2 to the n. And we're going to write it as x over 2 to the n. And again, those of you who have, misgivings about binary, you should just think of it as the base 2 version of, say 0.123 being 123 divided by 1,000. Okay. Should be more convenient. Okay. Now, let's think beyond this example. So one thing to note is that, you may have this many qubits, n qubits, but the phase that's encoded here is a bigger number. By bigger, I don't mean large in magnitude, but it actually has more precision. It has more digits. So more specifically, if instead of omega being x1 through xn for an n-qubit algorithm, omega could have point x1 through xm where m is bigger than n. Right? If it's smaller than m, it's fine. It just means that all of the rest of them are 0. But if it's bigger than m, if m is bigger than n, that means there's actually more information in the omega that you can compute. Right? Okay. What is discussed at length in chapter 7.2, but I'm just going to state the answer here, is that whereas if m is equal to n, you're actually computing omega exactly. If m is bigger than n, you're estimating it statistically. You're basically going to compute exactly the round off of omega to first n digits. And statistically, you can demonstrate that there's a probability distribution, and if you do it enough number of times, if you have the probability distribution, it peaks around the estimate to the first n significant digits. And that kind of makes sense. There's no surprise, but to actually prove that is technically, involved. And so those of you who want to see that, I refer to the book. So one thing that you might have noticed is that the ordering of the digits is swapped. You can go back and look at the magic formula or whatever. They're just swapped, and that means that the output that comes out, because routinely this is sort of the first digit and this is the nth. Whoops, just switch back to the pen. This is the first and this is to the nth digit. Whereas the way this algorithm works natively is that xn is stored in the first digit and so on and so forth. So all that means is we have to relabel them. Or we can do it by hand when the algorithm is finished, or we can just stick swap gates into it. That's not that interesting, but that shows up, say, in Qiskit when you have to program it. Now, the interesting thing that's going to be important for the next sort of algorithm and next sort of topic in this class is that what we've just done is the reverse of this operation. In other words, what has been done now is taking this state and pulling out x. But because this is a unitary algorithm, it's reversible, we can just run the algorithm in reverse. Right? Because the Fourier transform that we discussed at the beginning of this lecture is running this algorithm in reverse. So this is Q of t, and this is phase estimation. So these are really just two identical things, and when physicists learn about phase estimations, they're confused. Why is this a different algorithm? And so here's what I've done is just redraw the circuit diagram.